Artificial neural networks have also been used in visual applications. Most often, the neural network is used in a perceptual capacity, in a discriminative type of learning. Baluya's 1994 approach using neural networks to calculate the fitness function of a visual expression-based evolutionary system preceded most work in this area. The idea was simple: to learn from users' judgment. They did this by using a data-driven agent approach to teach the neural network to simulate the human evaluation of those images. There were 400 expression-based images, themselves generated using interactive genetic algorithm. Each image was rated by a single user with a general appreciation rating varying between -1 and +1. A multilayer perceptron was then simply trained to predict the fitness ranking of this particular subject on inputs of 48 by 48 pixel images. The authors tried and compared a number of architectures and improvements on the system. The technique yielded mixed results, likely because the technology and the amount of data available was simply not adequate to be successful at the time. Further examples of artificial neural network used for data-driven automatic fitness prediction for evolutionary systems include the work of Gédéon in 2008, which learned viewers' preferences among Mondrian's paintings and accurately predicted preferences when viewing new images in that style. Wolfer, in 2005, proposed a neurogenetic hybrid motif generator for computer graphics and imaging. Baluya, Machado, and Sanders have investigated the use of artificial neural networks for fitness evaluation with the goal of automatically generating interesting images. The network is trained to recognize and evaluate how interesting a given image is. Another example is DARCY, which stands for Digital Artist Communicating Intention. This system is designed to produce original images that could be considered creative. It was developed by Dan Ventura and his team. DARCY has been presented both as an artwork-making system with several public exhibitions and as a research project in computational creativity. DARCY takes a picture together with a set of adjectives as its input. It then generates a rendering of that picture that aims to reflect those adjectives. The generation process has two steps. The first step is to generate a pool of candidate renderings, and the second step is to curate a candidate. In fact, DARCY has also been used as a curator of an exhibition using only this second step. In the first step, a series of modules generates a pool of candidate renderings. First, the image composition modules generate an image composition. The adjective interpretation module consists of a neural network trained to associate adjectives with some 51 carefully selected image features. The image rendering module is a genetic algorithm that evolves a rendering. Each individual rendering is a sequence of Photoshop-like filters, and these rendering pipelines are being evolved. How a rendering fits the composition and the given adjectives is used as an automatic fitness function. The variety of renderings is ensured by introducing speciation through subpopulations in the evolutionary process. A number of sufficiently different candidates are selected by taking the best individuals from each subpopulation. This process constitutes an epoch and is applied several times to generate more candidates. After the first epoch described above, another artificial neural network trained to judge novelty checks the new candidates that are produced to make sure they are novel enough to be added to the population. To satisfy this criterion, the images have to be different from the ones produced until then. In the second step, once enough individuals have been generated, DARCY curates a single candidate. DARCY first selects the 10% of the candidate that maximize a similarity measure with the source image. This is to ensure that the source image is still recognizable in the resulting image. The candidates are then ranked by how well they match the given adjectives, and the top image is DARCY's final pick. There has been a formal evaluation study on how good DARCY was at evoking the adjectives compared to the production of humans operating under the same constraints, using the same type of filters with the same parameters. DARCY was rated to be at least as good as its human counterparts. Artificial neural networks were also used in art installations, for example, as controllers for virtual agents. The interactive installation Mimetic Starfish from 2000 by Richard Brown is a larger-than-life gold starfish whose image is projected onto a marble tabletop. The reactive agent architecture simulates muscle movements, and a neural network is in charge of the agent's behavior. The neural net starfish, as the author also calls it, reacts to human movements detected through a hidden infrared camera. Tentacles reach out towards slow movements of a hand, but if they move too quickly, it jumps back as it's startled. Stroking the skin of the virtual starfish triggers the firing of artificial neurons, producing undulations, quivers, and pulses of colors. As the reporter puts it, it is incredibly lifelike and responds to human contact by retracting disdainfully or stretching out a tentacle in friendship when a hand approaches. Australian artist Jonathan McCabe's piece, Nervous States, from 2006, consists of psychedelic images created by a neural network. Each image is a mapping of the state of the network, its connection, weights, states, and the dynamics onto colors for each pixel. McCabe generated a large number of pieces and selected 9 for this series. When using artificial neural network for generative art and computational creativity, there are still some issues. Learning is slow, computationally demanding, and sometimes complex. The data needs to be formatted and processed and needs to be made available for the learning to happen. Neural networks are also not very easy to design. Designing the exact topology, number of layers, and number of nodes per layer is not straightforward. Also, there are many parameters to decide upon. Neural networks are known to be black boxes, in that the learning is quite opaque. Given the distributed and numerical nature of neural network architectures, what the network is learning is not human readable. It is not like learning a grammar or learning a rule-based system. However, because neural networks are becoming so prominent as an approach to artificial intelligence, there is a lot more research being done with the goal of making them a little less opaque. On the other hand, neural networks also have numerous advantages. Once they are trained, they can generate new outputs very fast. They are very flexible for multidimensional domains like music, for example. They can encode vertical relationships between several voices pretty well. This is because they can be very large in the sense of taking a lot of inputs in parallel and automatically correlate them and learn dependencies. They are perfect for multimodal approaches since they do not care much about the nature of the data. And unlike some other approaches like the Markovian systems, they are not just a recombinant approach. They really have the power to generalize beyond the corpus if we do not overfit the data. They can capture the space of possibilities and model a given style and its statistical properties. They can then generate new instances within that style that are clearly distinct from what the corpus is made of. Finally, artificial neural networks are back in trend with representational learning, and we will learn more about that in our lesson on deep learning.